So welcome you back to today's module. So last couple of modules we were discussing about invariant statistical hypothesis of testing. So what we assume in these problems is that our testing problem has a nice structure. What does it mean is that your null hypothesis as well as alternative hypothesis are invariant. That means the probability distributions covered under the null hypothesis and the alternative hypothesis are invariant under the same group of transformations, which is G. Now, if that happens, I say that testing problem is invariant. Then we realize that if a testing problem is invariant, then it makes sense to consider only invariant tests. And then one can talk about finding the best invariant test of level alpha. And we named such a test as UMPI alpha test, or uniformly most powerful invariant test of level alpha. Then we considered an example of a location family. So testing that your data is coming from a location family against the alternative that it is coming from some other location family. We realize that in such a situation, for such a testing problem, UMPI alpha test exists, and one can use the Neyman-Pearson lemma to derive UMPI alpha test. Similar theory follows for deriving UMPI alpha test for testing whether a data is coming from one scale family against that it comes from some other scale family. So today we are going to deal with location scale family or affine family of distributions. So let us do that. So what we do is location scale family. So what you have is X, which is a data, x1, x2, xn. This has, suppose, PD of f. Now, you are interested in testing that f belongs to P0 against h1 belongs to h1 that f belongs to P1. Now, here P0 and P1 are location scale families. So what I assume is Pi. So they both are location scale families, but they may have a different functional form, different parameters. So Pi is collection of all those Fi, mu, sigma, such that mu comma sigma, which I can denote by theta, belongs to R cross 0 to infinity, which I can call as theta. And here I is between 0 to 1. So that means under P0, you have a location scale family F0 mu sigma. Under P1, you have another F1 mu sigma. So what I assume is this Fi mu sigma of x1, x2, xn is a location scale family. So I can write down this as F1 by sigma to the power n Fi. So this Fi is also different for h0 and h1. x1 minus mu by sigma, xn minus mu by sigma. X belongs to Rn, theta, which is mu sigma, belongs to theta, and I is between 0 to 1. So this could be a problem of the following type. Suppose you're interested in testing that your sample is coming from a normal distribution with unknown mean mu and unknown variance sigma square. So that could be your null hypothesis. Your alternative hypothesis could be that your sample is coming from an exponential distribution with location parameter or the guarantee time as mu and the hazard rate or the scale parameter as sigma. So it is some normal family. It has a distribution belonging to some normal, belonging to the normal family. Against that, it has a distribution belonging to exponential family. So here, F0 could be normal, F1 could be exponential. And then these are location scale families. So suppose you are interested in testing this. Now if you recall your estimation theory, you know that location scale families are invariant under affine group of transformations if your parameter space is whole R cross 0 to infinity. So if your parameter space is this, then any location scale family is invariant under affine group of transformations. So under P0 and P1, both would be invariant under affine group of transformations. So I consider G as collection of all those GABs such that A is positive and B is in R. And what is your GAB of x1, x2, xn? This is nothing but AX1 plus B, AXN plus B, where A is positive, sorry, for every x belonging to Rn, A positive, B is in R. Then you know that P0 and P1 are invariant under G from your estimation theory with induced group on PIS with induced transformations on Pi as what is the induced transformation? G bar of Fi mu sigma. So under Pi I remain in Fi only, except that under the transformation G bar AB, mu becomes A mu plus sigma and B becomes A sigma. So this is same as Fi of A mu plus B A sigma, right? So theta, which is mu sigma, belongs to theta. A positive, B belongs to R. So the testing problem is invariant. Invariant under this location scale or affine group of transformations G. So this suggests that I should consider only invariant tests. So first I try to look at what is the form of an invariant test. So a statistic T is invariant if and only if T of AX1 plus B, AXN plus B is same as T of x1, x2, xn for every A positive, B belonging to R. So you repeat the same thing which you did in the case of estimation problem. First you take A to be 1, then that means T of x1, x2, xn is same as T of x1, x2, xn. Sorry, T of x1 plus B, xn plus B is same as T of x1, x2, xn. Then I can take B to be minus of xn. So it becomes T of x1 minus xn, xn minus 1 minus xn, 0 is same as T of x1, x2, xn, which means T is a function of d1, d2, dn minus 1, where di is nothing but xi minus xn. Then what I do is I take B to be 0 and A to be 1 upon mod xn. So that means it will become T of x1, x2, xn. Now in D's there is no B, so only A is there, A would come outside. So it becomes x1 minus xn upon mod of xn minus 1 minus xn. So this, if you say, this implies that T of x1, x2, xn, which we did exactly in the estimation case, is T of x1 minus xn upon xn minus 1 minus xn, xn minus 1 minus xn by, sorry, I put this mod of this. First I put xn minus 2, xn minus 1 minus xn by mod of xn minus 1 minus xn. and you can put this as 0. So basically what I have done is I have taken b to be minus xn upon mod of xn minus 1 minus xn. I can take b to be this quantity because b could be anything in real line, and I take a to be 1 upon mod of xn minus 1 minus xn. So this is what happens. So this is some function of x1 minus xn upon mod of xn minus 1 minus xn, xn minus 2 minus xn upon mod of xn minus 1 minus xn into xn minus 1 minus xn upon mod of xn minus 1 minus xn. So what it means? It means it is a sum function of x1 minus xn divided by mod of xn minus 1 minus xn, xn minus 2 upon xn, mod of xn minus 1 minus xn, and xn minus 1 xn upon mod of xn minus 1 upon xn. So this is clearly a 1-to, this quantity is clearly a 1-to-1 function of x1 minus xn divided by xn minus 1 minus xn, xn minus 2 minus xn divided by xn minus 1 minus xn, and this loss quantity. Why? Because in either case, this quantity xn minus 1 minus xn upon mod of xn minus 1 minus xn is nothing but sine of xn minus 1 minus xn. Whether it is 1 if xn minus 1 minus xn is positive, minus 1 if it is negative. So in either case, I know this. If I know this, I exactly write down this in terms of xn minus 1 minus xn, because if I know the sign, then mod of xn minus 1 minus xn and xn minus 1 minus xn are 1-to-1 functions. So I can write down this is v of x1 minus xn upon xn minus 1 minus xn, xn minus 2, xn minus 1 minus xn. And this is nothing but xn minus 1 minus xn upon mod of xn minus 1 minus xn, which you can write down as w1, w2, wn minus 1. Now the only thing you note over here that wn minus 1 is xn minus 1 minus xn divided by mod of xn minus 1 minus xn. So it is a discrete variable. It will take value plus 1 if xn minus 1 minus xn is positive. It will take minus 1 if it is negative. Probability of this being 0 is 0, because probability that xn minus 1 is same as xn would be 0 because of continuous nature of the distribution. So wn minus 1 here takes two values, minus 1 and 1, depending on whether xn minus 1 minus xn is negative or it is positive. Now we know that it is ancillary. Under Pi. So that means it will have some distribution Fi star. That means now under P1 and P0, you are reduced to saying that H has a distribution which does not depend on mu and sigma. So ultimately you are left with dealing with testing simple hypothesis versus simple hypothesis, and you can use the Neyman-Pearson lemma to get the UMPI alpha test. So the only thing I need to find out, what is the distribution of W1, W2, Wn minus 1 under Pi. So what I have shown is, I have shown that any invariant statistic has to be a function of W1, W2, Wn minus 2, and Wn minus 1. Also, W, which is W1, Wn minus 2, Wn minus 1 is invariant. Why? Because you can apply Ax1 plus b over here. So when numerator and denominator both differences are there, so when you apply Ax1 plus b, b gets cancelled, and a comes common in the numerator and a also comes in the denominator, so a also gets cancelled. So it is invariant. So what does that mean? This implies that W is maximal invariant. That means any invariant statistic is a function of this quantity. So I need to find out what is the distribution of W1, W2, Wn minus 2 and Wn minus 1. So what I do is, W1, W2, Wn minus 2 and Wn minus 1 depend on x1 minus xn. So d1, d2, dn minus 1. So first I try to find out what is the distribution of d1, d2, dn minus 1 and divided by w1 and so on. So here wi is nothing but xi minus xn upon xn minus 1 minus xn. I is equal to 1 to n minus 2. So what I do is joint PDF of so you have a W1, W2, Wn minus 2, Wn minus 1. Wn minus 1, let me don't write down, dn minus 1. dn minus 1 is nothing but xn minus 1 minus xn. So what I do is I first write down here xn also. At point, let us say W1, Wn minus 2, s, dn minus 1 as s, and that as t. So let us look at what is that PDF. So what I have to do? In the joint PDF under pi, joint PDF is this. But I know that distribution of W1, W2. So joint PDF under pi is this for some mu and sigma. So what transformation I have to make? Let's try to do that. So what you have is x1. So here I make that transformation x1 minus xn upon xn minus 1 minus xn, or xi minus xn minus xn minus 1 is s for is wi for I is equal to 1 to n minus 2. That is what you are doing. W1, W2, Wn minus 2 at the point W1, W2, Wn minus 2. If I have to apply that transformation over here, I have to make xi minus xn upon xn minus 1 minus xn as wi. Then what you have is xn minus 1 minus xn as s and xn as same as t. So what do you get? That means xi is same as xn minus 1 minus xn is same as s wi plus xn. Xn is nothing but t for I is equal to 1 to n minus 2. Xn minus 1 is nothing but xn plus s, so which is same as s plus t, and xn is same as t. Now you can see that Jacobian is nothing but del x1 by del s, del w1, s would come, and so on as w. So it would be upper triangular matrix, but then this s would come at n minus 2 positions. So Jacobian turns out to be, and this would be 1, 1, and so on. So s to power n minus 2. Right? Upper triangular matrix, diagonal elements as SSS in the first n minus 2 diagonal elements, n minus 1 diagonal element as 1, and n diagonal elements as 1. So this is what this turns out to be. So what do you get? So under pi, the joint PDF of WW is, so this was the transformation, is, let me call this as hi star of W1, W2, Wn minus 2, s, and t, which is nothing but mod of s to power n minus 2 by sigma to power n fi. X1, you see, if you want, you can take sigma to be 1 and mu to be 0, because finally you will be finding out the distribution of W1, W2, Wn minus 2, which I know is ancillary, which does not depend on mu and sigma. So I can as well drop sigma and mu everywhere. So this is everywhere it is at mu is equal to 0 and sigma is equal to 1. because finally I know that this joint PDF of W1, W2, Wn minus 2 is not going to depend on mu I sigma. So this same as mod of s to power n minus 2 Fi x1. X1 is nothing but SW1 plus T, SWn minus 2 plus T, then xn minus 1 S plus T, T. This is what joint PDF turns out to be. And of course the ranges of SIs and Ts. So now I can get the joint PDF of W1, W2, Wn minus 2 and Dn minus 1 at points W1, W2, Wn minus 2 and S, right? So what I have to do is I have to integrate out the unwanted variable over here, which was xn, which was fixed at t. So I do that hi double star W1 Wn minus 2 S, which is nothing but I just integrate out t, so mod of s to power n minus 2 minus infinity to infinity Fi of SW1 plus t, SWn minus 2 plus t, S plus t, t, t. So I found out the joint PDF of W1, W2, Wn minus 2, Dn minus 1. Sorry, this would be Wn minus 2. So joint PDF of W1, W2, Wn minus 2 and Wn minus 1. Wn minus 1 is a discrete variable. It takes value plus 1 or minus 1. So it takes value minus 1 when Dn minus 1 is negative. Xn minus 1 minus xn is negative. So that means the joint PDF of W1, W2, Wn minus 2 and Wn minus 1 at point W1, W2, Wn minus 2 and Wn minus 1 is 1. Yes. So what I have to do is I have to see what is the probability that Wn minus 1 is 1. That means xn minus 1 minus xn is negative. That means Dn minus 1 is negative. That means S is negative. So this would be same as hi of W1, W2, Wn minus 2 minus 1 as minus infinity to 0, because that means xn minus 1 minus xn is negative. And then you can write down minus infinity to infinity mod of s to power n minus 2 Fi of SW1 plus t, SW n minus 2 plus t, S plus t, t dt ds. I convert this range into 0 to infinity, so that means I put s is equal to minus s. Now note that here s is negative, so mod of s would be same as minus s. So I can make the transformation minus s equal to s prime. So this becomes 0 to infinity minus infinity to infinity s to power n minus 2 Fi of t minus SW1, because I have put s as minus s, t minus SWn minus 2, then t minus s and t dt ds. Right? So what I do is I write down what is hi of W1, W2, Wn minus 2 and minus 1. So in terms of random variable. This is nothing but 0 to infinity minus infinity to infinity s to power n minus 2 Fi of t minus s. W1 is nothing but, as a random variable, x1 minus xn upon xn minus 1 minus xn. T minus s times xn minus 2 minus xn upon xn minus 1 minus xn. And then nothing but t minus s and t dt ds. Now note that here xn minus 1 minus xn is negative, right? Because you are talking about when wn minus 1 is minus 1, right? wn minus 1 is minus 1. So xn minus 1 minus xn is negative, s is positive. So I can make the transform minus s upon xn minus 1 minus xn as s prime, and I can again replace it back s prime by s because that would be integrating variable. Yeah, so how much it becomes? S becomes xn minus 1 modulus of xn minus 1 xn n minus 2. 1 would come through this Jacobian. So this becomes mod of xn minus 1 minus xn, which in this case you know xn minus 1 minus xn is negative. So it would be xn minus 1 to power n minus 2. But I have to keep it here mass 0 to infinity. Range remains the same because xn minus 1 minus xn is negative. So if s goes from 0 to infinity, s prime would also go from 0 to infinity. And then s to power n minus 2 fi t minus, so this becomes t plus. This has become s prime, so t plus s times x1 minus xn, t plus s times xn minus 2 minus xn, then t minus s, so t plus s times xn minus 1 minus xn, and t as it is, dt ds. Now you can see when it is minus plus 1 also, you get the same PDF. So similarly, hi of w1, w2, wn minus 2, 1. wn minus 1 is 1. wn minus 1 is 1, that means xn minus 1 minus xn is positive. So you do exactly the same thing over here, except that here because xn minus 1 minus xn is positive, so this s variable is positive. So joint PDF of w1, w2, wn minus 2, wn minus 1 at point w1, w2, wn minus 2 and 1. 1 means xn minus 1 minus xn is positive, so range of s is positive. So it will become from 0 to infinity everything. So over here. So now here s is already positive, so it is already s to power n minus 2. So it becomes t plus s times, so it is already t plus s times x1 minus xn and divided by that, and then you can put the transformations s upon xn minus 1 minus xn because here is positive as s prime. So you exactly get the same thing. This would be n minus 1, right? Because 1 would come from Jacobian. 0 to infinity, minus infinity to infinity, s to power n minus 2, fi of t plus s times x1 minus xn, t plus s times xn minus 1 minus xn, comma t plus s dt ds. So what your h naught has become that your h is same as h0, against that h1 is same as h1, because you have to consider only those tests which depend on observations only through w1, w2, wn minus 2 and minus 1. But their PDF only depends on h0 and h1. So it turns out you have to test simple versus simple. So what is the MP UMPI alpha test is phi x, which is 1. If you reject if h1 by h0 is greater than alpha. So because under h0 and h1, whether wn minus 1 is 1 or minus 1, it is exactly turning out to be the same thing. So it is 0 to infinity minus infinity to infinity, f1 of x, s to power n minus 2, f1 of t plus s, this is same as d1, t plus s times dn minus 1, t dt ds divided by 0 to infinity minus infinity to infinity s to power n minus 2 f0, that is under h0 of t plus s t1 t plus s dn minus 1 t dt ds is greater than c 0 otherwise, and where how this c is chosen so that this expected value of phi x is exactly alpha. Under f0, mu as 0, sigma as 1, so f0, 0, 1 of phi x, which is same as expected value under h0 is alpha. So this gives you UMPI alpha tests. So what we did is we saw that restricting to the class of invariant tests is certainly beneficial in certain situations, especially in last 3 examples where we tested whether a distribution belongs to a family against that it belongs to some other family of the same type, whether it is a location family, scale family, or location scale family. So we could derive the test. Now what we see is invariance also reduces the data, because that is what invariance is doing over here. For example, in this example, we saw that if you apply invariance, it says that you need not consider whole data, rather you should consider only data through W1, W2, Wn minus 2, and Wn minus 1. So it is reducing the data. So there is a reduction of data through invariance also. There is a reduction of data through sufficiency. So now question is whether we first apply reduction of data through sufficiency and then apply invariance, or first we apply invariance and then see what happens, whether the two approaches are same. And that is what we'll discuss in the next module. So thank you very much.